In this example, we'll look at a proof by induction. This is just an overview so that you'll be familiar with the approach. We won't use the method too much in this course. So we want to prove that the sum of integers from 1 to n is equal to n times n plus 1 on 2. In lecture 2 we'll prove this using a direct proof. But for now, let's look at the steps we go through. So we have a proposition, an, that holds for all natural numbers n. First thing we do is check that it holds for n equals 1. Then we take some arbitrary number k and assume that ak is true. We derive a proposition for n equals k plus 1 and see if that's true or not. If it is true, then we've proved our proposition by induction. We have our proposition, Sn. It's the sum of numbers from 1 to n, and that's equal to n times n plus 1 on 2. Let's see if it's true for n equals 1. If n equals 1, then n times n plus 1 on 2 is equal to 1 times 1 plus 1 on 2, because that's equal to 1. We've proved that. Maybe that's a little bit easy. Let's look at n equals 2. N equals 2. Then n times n plus 1 on 2 is equal to 2 times 1 plus 2 on 2. Well, that's equal to 3. And that's equal to 1 plus 2. We can give that a big tick again. Now we assume that sk, so n equals k, is true. It's sk, and that's true. We want to find sk plus 1. Well, when n equals k plus 1, sk plus 1 will be equal to, of course, sk plus k plus 1. Sk is equal to the sum of numbers from 1 to k, and then we add k plus 1. That's equal to k times k plus 1 on 2 plus k plus 1. Let's put those two terms onto a common denominator. Now we have two terms on a common denominator. We can combine the numerators. We can expand that first term and then collect like terms. Next week we'll look at quadratic functions, and we'll see that we can easily factorise that numerator. So here we have a simplified formula for sk plus 1. Now we can see that that's equal to n times n plus 1 on 2 for n equals k plus 1. Having demonstrated our proposition is true for k plus 1, we conclude that it's true for any n.